So we're jumping into organic derivatives, and all the word derivative means is to change. And so what we've been learning about are basic organic compounds and molecules, and what organic derivatives are is just a change from those. And what you'll notice is for each one of these 4 organic derivatives that we're going to cover, they each have a unique piece to them. Either it's a piece that's been added in, or it's been changed somehow, or sometimes things have been taken out. We'll go through the details of each one as we get to each organic derivative, but you can see here that each organic derivative contains what's called a functional group. And they're listed up here on the board in quotation marks. So halides contain a halide functional group, and then hydroxyls, carboxyls, and ester linkages. And we'll talk about each one of those. So in the next clip upcoming, I'm going to jump into the first one, which is halides, and talk a little bit more in detail about what they are, what they look like, and how we can name them. Okay, so let's take a look at some naming of halogens or halides that contain a halogen functional group. As you can see here, I've got some examples on the board, just some basic organic molecules, and the naming is really similar to that of just regular alkanes. What we're really treating the halogen functional group as is just a branch, and they basically follow the exact same rules as alkyl branches do. So when I name this compound, for example, I'm going to number the parent chain so that the halogen functional groups receive the lowest number possible. So in this case, I can number this left to right or right to left. Either case, this fluorine atom is going to get the number 2. Now, when I name these halogen functional groups in an organic molecule, they have just a little bit of a slightly different name. So fluorine atoms, we call those fluoral in the organic name. Chlorine atoms, we call those chloral. Bromine atoms, we call those bromo. And iodine atoms, we call those iodo. And so you can make note of that, how that's written in each of these. The spelling is important, so make sure that you spell those appropriately. So because this fluorine atom is sitting on carbon 2, this is going to be 2 fluoral, and then the name of the parent chain, which is 3 carbons long, so propane. Notice, just to point out as well, that these dashes that are empty, these would contain hydrogens. I'm just not writing them in just for the sake of the compound kind of being too cluttered and things like that. But they're there, so just recognize that. Now for this one right here, we've got a parent chain of 4, so my parent chain should be called butane, and it is. But I've got kind of 2 options here. I can number this left to right and give the chlorine atoms both a 1 and a 3, or I could number it right to left and give the chlorine atoms a 2 and a 4. Obviously, if we're going to follow the same rules as alkyl branches, then this one is not going to be correct because that is a higher set of numbers than 1 and 3. We want to select the lowest set of numbers. So 1, 3, and then we say dichloral, just because we've got 2 chlorine atoms in the molecule, butane. And so that's the correct name for this guy. For this one right here, sometimes we get parent chains that are really small, like ethane, and so how we number this doesn't matter. And if it doesn't matter, the bromine is always going to have a number 1. For example, in this case, then I don't call this 1-bromoethane, I just say bromoethane. So you may see something like that as well as you kind of work through your practice. The last one here is you can see multiple occurrences of different halogens within the same molecule, and that's as complicated as they'll get. You won't ever see double or triple bonds in these guys as far as naming them goes. That's for more advanced high school or university type of course. But for these guys right here, this is as complicated as you'll see it. So you can see in this one I've got some bromines and some iodines. And so the way that I do those is, again, I have to alphabetize them. And alphabetizing them based on the first letter of the actual halogen group, not the prefix, in this case di. Now this one, it doesn't really matter, but it can matter if you, for example, stick a di-iodo in a di in front of an iodine or something like that. It could potentially change how you would alphabetize it. So we don't use the prefix, we just leave it as is. Alphabetize it based on the first letter of the actual halogen name. And so B comes before I, so I alphabetize it like that. Now, I want to number this again so that the branches get the lowest set of numbers. Left to right would give me a 1, 1, and a 3. Right to left would give me a 1, 3, and a 3. So 1, 1, 3 is a lower set of numbers. So that's what I go with, and this ends up being 1,1-dibromo because both bromines are on carbon number 1, 3-iodo because the iodine is on carbon number 3, propane because that's the parent chain name. So now that we've covered halides and how to name them, we're going to go through some chemical reactions that involve halides, or chemical reactions that will make halides. So the first one that we're going to cover is what's called an addition reaction. And you can just add these to your reaction page that you should have in your notes so that you can keep all of your chemical reactions in one spot and be able to review them easily. Addition reactions are very, very fast. And it's because we have an alkene as one of the reactants. And if you remember, alkenes are unsaturated molecules, which means that they have a carbon-carbon double bond located in them. And anytime a molecule that's unsaturated is presented with an opportunity to become saturated, it's going to do that, and it's going to want to do that very, very quickly. And so you can see my template that I've got written here, which is just some alkene reacts with a halogen to make a halide, and that's essentially what an addition reaction is. So in this one example here that's fairly simple, we've got propene. You can see the double bond that's located right here. It's reacting with a halogen, and that halogen attaches to the site of where the double bond is. You can notice that these two chlorines don't end up on the same carbon. One chlorine ends up on one carbon and the other chlorine ends up on the other carbon. And that's important in terms of making sure that one carbon doesn't have too many atoms around it, violating the octet rule, or the other carbon doesn't have enough atoms around it, also violating the octet rule. Each carbon needs to have 4 bonds around it. And so that's something that you got to watch for. And then we can name these halides here. You can see the name that I've written down below, 1,2-dichloryl propane. Notice that this is now propane because these are carbon-carbon single bonds, and so the parent chain is now considered an alkane, not an alkene, like propene was over here. And so that's also something you need to watch out for. Propene is going to, reacting with chlorine, is going to turn into 1,2-dichloryl propane. Oftentimes I see kids make mistakes and they'll keep this as propene, and that suggests that there's a double bond there, so you need to make sure that you're watching out for that mistake. The last thing that sometimes you can see is if we do an addition reaction, sometimes I can have, instead of chlorine here, I can just have like hydrogen. And if I have hydrogen there, this is also an addition reaction. These hydrogens will just attach to this spot, and instead of chlorines here, I'll have hydrogens. And then it's not a halide, it's just a regular alkane. This would be propane, and you're done with that. One other type of addition reaction that you might see as well is you might see sort of a hybrid between the two. So some kind of acid. So let's say that we had hydrobromic acid, HBr. Again, same thing, this H and this Br would attach at the site of the double bond, and so we would get an H and a Br here. Now, the interesting thing about this is if you have this kind of a reaction with this acid here, HBr, you're going to actually get some isomers out of this, because you could get an H attaching here and a Br attaching here in some cases. And in other cases, you could get a Br attaching here and an H attaching here. And so some molecules might be 1-bromopropane and other molecules might be 2-bromopropane. And so those are isomers of each other. They do have different names but the same chemical formula. And so it's also just something you need to watch out for as it relates to addition reactions. Substitution reactions. The thing that's really different about these guys compared to addition reactions is that these reactions are very, very slow. So we need a catalyst to kind of make these go. And anytime you have a chemical reaction with an arrow like this and something written up above, that's the catalyst that's being used. So some real common catalysts that are used in chemical reactions are UV light, like in this substitution reaction, or sometimes sulfuric acid, just H2SO4 aqueous is another really good catalyst. If you think about the name of these two reactions, addition reactions and substitution reactions, and you kind of relate it to sports just in general, if you're adding players to a field, you're going to increase the number of players on the field. If you're going to substitute players on a field, you're going to keep the number of players the same. And so if we're thinking about this sort of larger molecule here as the playing field, you can see that when I from my start to the finish, from the reactants to the products, you can see that the playing field here is the same number of atoms in that molecule. The only difference is that now we have a different atom on or in that molecule, or on the playing field, if you want to kind of use that analogy. And so for substitution reactions, we have an alkane, some kind of carbon-carbon single bonded sort of molecule reacting with a halogen in the presence of some kind of catalyst to kind of force this reaction to go a little bit quicker. And it makes a halide and then some kind of acid. And so if I'm using this example of propane reacting with bromine, then what I'm going to get is I'm going to get bromine that's going to attach on either one of the end carbons, and I have another isomer here that I could write down but I didn't, that I want you to try and figure out on your own. So see if you can't write down what the name of this molecule is, and then draw out what the isomer would be that would be made, as well as the name of that isomer. Remember that isomers have the same chemical formula but a different name. And there's only one other isomer that can be made out of this reaction. So it should be not one where you're kind of thinking of, are there like 8 isomers here for this? It's just one more. And then the last thing is that we create an acid over here. So really essentially all that's happening, if I were to kind of draw an arrow with this, is I just have that atom and that atom switching places, or substituting one for the other. And so this bromine comes in, substitutes the H out, the H comes over here and attaches itself with the other bromine here that's left behind, and that's how we get our hydrobromic acid as one of the products on the end. And that's what you need to know about substitution reactions, guys.